Good morning, physics students. It's Monday, 3:30, 2020. Let's do some physics. So today, we're going to practice some friction problems on an inclined plane. So we've done some forces where we said the force was at an angle compared to the object. But now we're going to put an object on an incline, and we have to look at how the math is going to play out. I'm going to use as our demonstration problem number 8 from that page 85 copy that I gave you from the old book. You should have paper in front of you. You should be working through this as I talk about it. Stop the video once in a while and do your work so that you are processing this as we go. Our problem says we've got a 3 kilogram wood box, slides from rest down a 35.0 degree inclined plane. How long does it take the box to reach the bottom of the 4.75 meter wood incline? The problem as it's written on that page says refer to some table for the coefficient of friction. And what you would have had to do is recognize that it's telling us that the box is made of wood and the incline's made out of wood, and we have a table with some coefficients of friction, and you find out that the coefficient of sliding friction, wood on wood, is 0.30. Okay, so that's our mu. We are looking for, right here's our question. How long does it take? So that means we're looking for delta T. Other things that we know, right here, 3.00 kilograms, there's a mass. 4.75 meters, that sounds like a distance. We have an incline, 35.0 degrees. Oh look, it slides from rest. That means VI is 0. So that's just kind of analyzing the problem, what we're looking for, and what we know. Let's also just kind of remind ourselves, what do we have to work with? Well, this problem involves friction. So whenever we have friction, remember the coefficient of friction is the frictional force over the normal force. It's the ratio of the force of friction to the normal force of contact between the surfaces. Other things that we know that we're dealing with right now. Newton's second law says F equals m times a. And, of course, we have our regular arsenal of equations that we dealt with for velocity problems, like, I don't know if I'm going to, I guess I'll write them down again. Vf equals Vi plus a delta t, delta d equals Vi delta t plus 1/2 a delta t squared. Vf squared equals Vi squared plus 2a delta d. So that's all stuff that we have to use. That's in our toolbox to attack our problem. Well, I'm combining metaphors now. I used to refer to an equation list as a toolbox, and then I thought it was more fun to refer to it as our arsenal. These are the things in our arsenal. Okay, so I'm looking for a time. Well, obviously I'm going to have to refer to these equations for a time. The box starts at rest, but then it moves down the incline, so obviously its speed has to change, its velocity has to change. So there's got to be some acceleration in there. We know the mass of the box I better draw a picture. Here's my incline. Here's my box. I know that box has a mass of 3 kilograms. Didn't turn out very good, but that says 3.00 kilograms. I know that the slope is 35.0 degrees. So let's draw in our forces. I'm going to change color here. First force that you basically always want to draw is your weight, because we know what direction weight is. Weight is always straight down. Now, I wasn't given a weight, and I need you to get this into your physics mind. Mass and weight are related, but they are not the same thing. If I have a mass, I can find a weight, provided I know what planet we're on, and I think our problem is done on Earth. Weight equals m times g. Okay? Now, the box can't move in that direction because the incline's in the way. And so to describe the motion or the forces on the box, what we need to do is replace this force with 2 forces that are going to accomplish the same thing. And so that's where I'm going to come up with, if I go from my tip of my arrow perpendicular to that incline, then this part of this triangle I'm going to label as F sub P for the parallel component of the weight. And then this part is going to be called F, and I use like an upside down T for my perpendicular symbol. I've seen that somewhere along the way. That's what I use. Okay? Now, we know that the box is accelerating this way, so this guy's going to be out of balance. We know that the box isn't moving into the incline or off the incline, so that force has to be balanced, and it's balanced by an equal and opposite normal force. So the normal force in this case is not equal to the weight. If I'm standing here in the room on a flat floor, the normal force of contact between me and the floor is equal to my weight because the floor is supporting my entire weight. But in this case, if I'm on an incline, if I'm on a hill, my weight's pulling down, the hill's only pushing back with the perpendicular component of my weight, not my entire weight. Because part of my weight's making me try to fall down the hill. And that's what's happening here. We've got friction involved because this box is sliding, and we know that friction always opposes motion. So this force is trying to make the box move that way. So friction is going to be that way. And if I look now, I think that's all my forces. So the original force was my weight pulling straight down. I'm replacing that with these two, perpendicular and parallel. The perpendicular component is balanced by the normal force. Friction is opposing the parallel force. Now, without really thinking about it, I drew my friction almost as big as I drew the arrow for the parallel component, but we know that the box is moving down, so that means friction is going to be less than the parallel component. Okay? All right. I need to possibly do one little correction over here. This F equals ma, that force is called the net force. Okay? And the net force is something that I can't give you one set equation for in problems. It's equal to ma, but there may be lots of forces acting, and when you have to figure out the net force, you have to do some physics reasoning. So in this case, I think about it and say, all right, I know the box is going down the incline, so that parallel force component must be a little bit bigger than my frictional component. So my net force is going to be whatever my parallel component is minus the part that friction is holding back. Okay, the net force is what's left over. All right. So that is an equation that, again, you have to reason out with each individual problem. In addition to all this stuff, I could have outside applied forces acting in here, and they might come into play on that net force. All right, I think I'm ready to get into the math of the problem. Remember, we're looking for a time, and I think, let's see, we've got a time, and if you look at this one, we don't know the acceleration, we do know initial velocity, we don't know the final velocity. So, this equation, it's not helping us a whole lot right now. We also know displacement, and we know the initial velocity is 0, so this crosses off. So, this one at least only has 3 variables left. I'm looking for delta t, but I don't know a. I do know delta d. This one, this guy's gone. I know delta d. I don't know a. I don't know f, vf, and there's no delta t in it. So my thought is this middle equation right here is probably going to be our best bet for how to find delta t. There's one thing I don't know, though. I don't know the a. So I'm going to have to find my acceleration from this other information. My acceleration would be the net force over the mass. Okay, so can I find my net force? My net force is going to be my parallel component minus my friction. Can I figure out the friction? Well, the friction would be the coefficient friction times the normal force. And the normal force is equal to the perpendicular component. I just did a lot of reasoning, and you might need to back up and replay that a few times. But in my mind, when I figured out something that I knew already, I'm going to have to find the parallel and perpendicular components probably as a starting point. Okay, so the incline was 35 degrees. I'm not going to get into geometry proof here right now. I want you maybe trust me on this a little bit. That angle is the same as that angle. And, okay, I'll get into a little bit of the geometry proof. If you see that this line, the weight is perpendicular to this horizontal line, and my perpendicular component is, my perpendicular component is perpendicular to the incline, so that somewhere along the way, and I guess I don't know the exact correct math terms to use, but that angle has to be the same as that. This line's perpendicular to this one's perpendicular to this one, so the angle between those lines has to be the same as the angle between those lines. So that's the angle of our incline is equal to the angle between the weight and the perpendicular component. Remember, I could draw the parallel component also down here. I can always move, I can think of a vector moving parallel to itself. So I like this triangle right here. Try a different color. Because in this triangle, we've got a right triangle. I've got an angle. I know it's 35 degrees. And I know the weight. Well, I don't know the weight. I can find the weight. So let's do that. Fw equals m times g. So Fw equals 3.00 kilograms times 9.80 meters per second squared. So the weight, 3 times 9.8, get out a calculator. If I weren't tired, I stayed up rather late last night grading papers, I could probably do that in my head, but the calculator's right here. 3 times 9.8 is 29.4. Yes, I should be able to do that in my head. Kilogram times meter per second squared is a, oh, I hope you chimed in with Newton. Okay, there's my weight. Okay, now, I got to find the components of my weight. So, components. The parallel component is opposite my angle, and so when I think about the opposite, I have the sine function. I should have said in our arsenal over here we have trigonometry. Okay, so I know that sine of my angle theta equals Fp. Sine of this angle is the opposite over the hypotenuse. The hypotenuse is the weight. So therefore I can say Fp, the parallel component, is going to be my weight times sine of theta. So my weight, we just figured out, was 29.4 newtons times sine of 35. 29.4 times sine of 35. $16.7 newtons. Now, my perpendicular component, if we've practiced our components, we know that it's going to look just like this formula. It's going to be the F of the weight, the force of weight, times the cosine. So to get one component, use a sine. To get the other component, it's going to use cosine. So I have 29.4 newtons times cosine of 35.0 degrees. 29.4 times cosine 35. That's 24.1 newtons. Okay? So I have my two components figured out. Let's go back up here again with my components. So now, let's see what else I can do. I'm going to jump over here. I need to know my friction, and I can get my friction from this. If mu equals the frictional force over the normal force, then the frictional force equals mu times the normal force. What's the normal force? Well, remember, the normal force is the opposite direction, but it's the same magnitude as our perpendicular component. So our directions are kind of figured out from this diagram here. We're going to do the math basically with just, for the force part, by reasoning out the magnitudes and doing our math with magnitudes. When we do our acceleration, we better include sine. So I'm coming down here, just extend the page. If mu equals frictional force over the normal force, and let's see, so then the force of friction equals mu times the normal force. But the normal force is equal to the perpendicular component, so we got mu times the perpendicular component, which means that the friction is, our coefficient of friction was 0.30 times the perpendicular component, make sure I get the right one here, 24.1 newtons. All right. 24.1 times 0.3. 7.23. We only got 2 sig figs, so I'm going to write down 7.2 newtons is my friction. Okay, we're making progress. We're calculating something. We haven't got to what we're looking for yet. But here's where I'm going to pull in this net force thing. And I'm going to just talk you through that again. Remember, net force is the overall of what's happening. We know the box is sliding down the incline, so we know that the parallel component is more, and the parallel component is going to be reduced by whatever the friction is holding back. So my net force is the parallel minus the friction. F net equals parallel force minus the frictional force. So that equals parallel component. We come up and find that 16.7 newtons. Minus the frictional force, 7.2 newtons. 16.7 minus 7.2. Let's see, 16.5, so that's 9.5 newtons. There's our net force. Okay, if I have net force, net force equals mass times acceleration. So acceleration equals net force divided by mass. I just got my net force of 9.5 newtons, and the mass was 3.00 kilograms, so my acceleration is 2 sig figs, 3.2. Let's see. A newton, remember, is a kilogram times a meter per second squared. So kilograms actually cross off, and I'm going to be left with meters per second squared. I've got an acceleration. So, oops, that's not the right button. There we go. If I've got an acceleration, delta D equals 1/2 a delta t squared. Delta D equals 1/2 a delta t squared. So multiply both sides by 2, gets rid of that. Divide both sides by a, gets rid of that. Take the square root of both sides, gets rid of that. Delta t equals square root of 2 delta d over a. So delta t equals square root of 2 times, what was the length of our ramp? 4.75 meters. Divided by acceleration, which we just figured out right here as 3.2 meters per second squared. The meters are going to cross off. Second squares flips back to the numerator. Bring it out of the radical, and we have seconds. Our labels work. If our labels work, I feel pretty confident that we did the problem right. Delta T equals, okay, now, home stretch. I'm going to take the square root of 2 times 4.75 divided by 3.2. Close your parentheses, hit enter. My time was 1.7 seconds. Wasn't that fun? Talk about a good mental exercise. Now, I only had 2 hours sleep last night, so I'm feeling a little slow today. But that's a good stimulator, and that's the way you need to try to think about it. This is like doing a puzzle. You have to try to put the pieces together. You can't just look at it and say, "I don't know the answer," and quit, because I don't mean this at all insulting, but I don't think there's a person in this room that can just look at the problem I gave you and know the answer. There may be people out there in the world that can do that. I haven't met one yet. What do? You sit down and you start just kind of putting pieces together to see what works. Now, this whiteboard is not a very good format for working physics problems. On a piece of paper, I can lay this out a little bit better, and I can see things a little bit better, and I can see everything all at once. And I might have my equation sheet close by. I don't have to take up room with that. You need to make a decent diagram. The diagram helps you see the relationship between forces. And if you make one of these tiny little diagrams in the corner of your paper, it doesn't do you much good because everything's so jumbled together. Honestly, this one is too jumbled. It should be bigger. But I knew that working on the whiteboard here is a bit of a problem. I didn't have an equation that got me to the answer. So I start out with just some basics like, hey, I got an incline. The weight's pulling down. It's not pulling along the incline. We probably need to know the components. We need to know the component forces. In this case, not horizontal and vertical. We need to know parallel and perpendicular. We need to apply a free body diagram, say what other forces are in play. Normal forces balancing things out, but friction always opposes motion. That's going to be key. You have to think about which way to draw your friction. If I were applying a force to push this crate up the ramp, think about what that's going to look like. I'll just draw that in real quick. Let's say here's my incline. So of course, I've got weight acting down, and part of the weight is pulling this way, and part of the weight's pulling this way. Okay? Now, if I apply a force to push this crate up, I say this is force applied, and here's the force parallel. Now think about it. If the applied force is bigger than the parallel force, then the net force is upward, right? If the net force is upward, friction always opposes motion. So the friction, in this case, is going with the parallel component. And so if I know I'm moving this up the ramp, I might write my net force equation as my applied force. Something in the problem told me that we're pushing it up the incline. So I got my applied force minus these things that are holding back. And what's holding back is the parallel component, and also what's holding back is the friction. I told you, there's no one set equation for the net force. You have to analyze the question at hand. If you noticed, I'm missing a force yet. This was my perpendicular. So the normal force is always perpendicular, equal and opposite to that perpendicular component. We know that the box isn't going this way or that way. The box has to move along the incline. So I'm only doing that one example problem. You saw it was pretty in-depth, and your assignment today is only going to be 3 problems to try to work on. I am also going to get you your Chapter 4 problem set that you might start. Hopefully you've practiced enough that you're ready to start getting into the graded problems. If you are stuck on anything, you need to tell me. You need to let me know. I will certainly address problems. I have solutions to the page 85 problems online, and I don't have solutions to the higher numbered problems from page 63 yet. I'm hoping to get some of those posted today. I guess that's it for today. You guys stay safe. Maybe pop in sometime on a Google Hangout or whatever when I do some of those meetings. I'd like to see your faces again, right? Take care of yourselves.